So thank you, Anma, for the chance to talk here at this seminar. So you asked about habilitation. Well, that's a typical thing in many European countries, not only Germany, which you do 6 years after the PhD. And then this allows you to become professor. So comparable here, it would be the transition between assistant and associate professor, kind of. Okay, so my talk is about cancer metastasis. I'm going to share my screen in a second, but first I'm going to say a few words. Because I find it very hard to focus on cancer in these times of coronavirus. The thing is, I think all of us here in this audience are mathematical biologists, and we understand epidemic models really well, right? We know what an SIR model is, we know what R0 is, we know what flattening the curve means. So the discussion in the media touches us, right? We understand what people are talking about. And we also understand what a model can do and what a model cannot do. So I think it's very natural for us to be involved, to be absorbed in all this discussion. On the other hand, cancer continues, right? Cancer exists in the same way as it did before. People suffer, people die. So let's focus on cancer and cancer metastasis. So now I'm going to share the screen. Yeah, all right. So you all should see the wonderful picture of Adam. Adam is a PhD student at the U of A, and he worked with me on this. Okay, so metastasis is responsible for 90% of cancer death. And that's the reason why many people say that this is a late stage cancer or late stage of the disease. But it's actually not true. So Hanin is a colleague from Idaho. He has shown that metastasis can arise rather early. They can even arise before the cancer is detectable. So in some cases, the metastases are already there, and they do not just show up at the later stages. But of course, then there are other cancers where they do show up in later stages. Let me quickly introduce the standard understanding of metastasis, which is the metastatic cascade. So I start with a whole bunch of tumor cells somewhere here, and then I need some vasculature. So maybe there are some blood vessels which are connecting to the cancer, but then they also might be connecting to other parts of the body. And let's say here is an organ, maybe a liver or something, and then this connects here as well. So cancer metastasis has many stages. The first stage is that the tumor cells enter the blood system. And there are two ways they can enter the blood system directly if the tumor is vascularized, or they detach and then move towards the next blood vessel and then intravasate into the blood system. Intravasation. Okay, then they can be transported through the blood system. And then there are again two ways how they can metastasize. One is that they just get stuck in very tiny capillaries. They just get stuck there. And instead of dying, then they start growing, and then they form a metastasis. Or the other way is that they actively leave the blood system and invade a new tissue and then form a metastasis somewhere else. So that's extravasation. And then each of these processes, so you can divide it into 5 steps, if you like, have been studied a lot with modeling and with, of course, experimentation and observation. So let's take this understanding now and look at some of the phenomena which are associated to metastasis and see how far this understanding will bring us. So I'm asking questions why? Why do metastases show the following curiosities? And here is one. Often they go to the bone, to the lung, to the liver. Actually, there seem to be certain patterns. So for example, prostate cancer would certainly often go to the bone, lung, and liver. Breast cancer often goes to the brain as well. And yeah, okay. So there are certain patterns for certain metastases. Another observation is metastasis can lie dormant. I said initially that it is entirely possible that metastases arise early and you don't see them for 10 years, 12 years, 15 years, and only then they show up. So they can lie dormant for a very long time, and then for apparently no reason, then they start growing. Another common observation is that if the primary tumor is removed, that then the metastases start growing all of a sudden. And this is called the metastatic blow-up. So they seem to be waiting for whatever signal or whatever, and then when the primary is removed, then all of a sudden they grow. And of course the question is why? Why does this happen? Another interesting observation is metastasis to sites of injuries. So there are reports of dental patients who went to the dentist and got a dental surgery and had cancer somewhere else in the body, and then they would form metastasis right there where the surgery happened. And that's very curious. There's also this story of Terry Fox, who we all in Canada know and love. And there's also discussed, I mean, he had, in a car accident, he had an injury in the leg while he had already lung cancer. And then right at the injury location, he formed a metastasis. Well, no, I should be careful. He formed bone cancer. And it is not clear if this came from the lungs or if it was an independent event. Okay. Metastatic relate to chronic inflammation. So that can be found in people who have chronic inflammation issues. And then also, metastases sometimes do not react to immunotherapies. Right? I think many of us know that immunotherapies are a new hope against cancer. The idea is you take out immune cells from the system, you identify those which fight against cancer, and you amplify them, and then you put them back into the body to have a higher killing rate to the cancer. So this does work in many cases. It does not work in some cases. And of course, we are interested to understand why it does not work in some of these cases. Okay. Now, looking at these, going back here, looking at these, how many items are these? 6. The last 3, they all have to do with the immune system. Right? So injuries, of course, the immune system is active, inflammations as well, immunotherapies as well. So this list already indicates that we have to look at the immune response and see what the immune system does with the cancer. And for me, this research started with Laili Shahriari. She is now assistant professor at the University of Texas. And I met her, I think, in 2015 at the MBI in Ohio, and we talked about metastasis. And she told me something which I found interesting and I've never heard before. Because she said that actually the immune response might be responsible for the metastasis. So the immune system might not only kill cancer cells and keep us healthy, it might actually be that it is instrumental in forming metastasis and helping the cancer to grow. In particular, what she found after reading millions of papers is that there are adapted immune cells, which I will call later educated immune cells, which have been adapted by the cancer to work in the favor of the tumor. Yeah. And so this paper in F1000 Research is a very good summary or review about existing literature. It does not contain a mathematical model yet. So then I set out with Adam to try to come up with a mathematical model. Okay. Here is an interesting paper from Nature 2005. So it's already relatively old. But it shows this effect already. If you look here at the lower graph, so down here is time. And then in a tissue sample, they measure 2 types of cells. They measure immune cells, which are the green ones. And then they measure cancer cells, which are the red ones. And you see in the time course that in this tissue, the immune cells come first. The immune cells come first, and then the cancer cells settle where the immune cells are already. And you can see that here in the last graph, right here, you see a cloud of green cells, which are the immune cells, which is then seeded by a cancer. And so it's a very clear indication that the immune system kind of prepares a niche or seems to make something which tumor cells actually like. Okay. So here's a paper from 2015 about inflammation-mediated metastasis, so making a very strong connection between inflammation and metastasis. Here, this is primarily related to the epithelial to mesenchymal transitions, so the EMT. And then here, a few more papers, immune cell promotion of metastasis, where this is discussed. So let me maybe give you two examples of the details now, how this works. So here's one. So the skull thingy is a cancer, and I like to talk about macrophages. So macrophages, the first part of the innate immune system, and the first actors are the M1 macrophages, and they eat everything foreign. So these are the good guys. But if this would be a healthy wound healing procedure, then at some point you have to shut down the M1 macrophages so that the wound can heal and that the destruction of cells stops. And this is what the M2 macrophages do, so they come a little bit later. And they produce growth signals so that the tissue can regenerate. But in the cancer case, these growth signals can also be used by the tumor to happily grow. Then there are tumor-associated macrophages. I'm not quite clear if the M2 and the TAM, if these are indeed the same. So different literature calls them a little bit differently. I keep them separate for now, which also then, so the tumor-associated macrophages, they can increase motility of the cancer cells. They can prepare niches for metastases, and they can even increase angiogenesis by releasing angiogenesis signals. So these are all macrophages, but the M1s are the good guys, the M2 and the TAM are the bad guys in the context of cancer. Another class, part of the adaptive immune system, are T cells. They're the cytotoxic CD8 plus T cells, which would attack the cancer. And then the regulatory T cells, which then stop the attack and protect the cancer. And there are many more examples. So I think I have maybe two more. Yeah, the platelets. Platelets are discussed in this context of metastasis as well, because they can form blood clots around circulating tumor cells. So the brown ones here are tumor cells, and then they're surrounded and also then protected by the platelets. And the platelets even release growth factors, which then can make the cancer cells happy again. So I think the platelets play an important role in this transport mechanism. And then for lung cancer, there's cancer-associated fibroblasts, which increase the cancer growth, which increase angiogenesis, which increase invasion, and which even increase drug resistance. So the picture which comes out of all these studies is that the immune system is really a bad cop, good cop, bad cop situation. So some immune cells help you, and I think in the majority of cases, the immune cells would successfully eradicate a cancer before you even see it. But not all cops are good, so some are compromised, and some immune cells are compromised, and then they might actually help the cancer to grow and to metastasize. Yeah, so this reiterates what I basically said already. So before I present our model now to address this issue, I like to review a little bit previous modeling approaches. The first thing people did was stochastic models. And this is, I think, a very good, very natural approach, because metastasis is stochastic, right? You cannot predict with certainty where they go and where they show up. It is really a random event. And so stochastic model seems to be the right language for this. There's an early paper by Liotta, 1977. And then Alexandra Mishor has written a whole bunch of papers about the metastatic phenotype. Hanin, I mentioned at the very beginning, he looked at the natural history of metastasis, and he was the one showing that the metastasis can arise rather early in the disease. Together with Chris Fry and also with Adam, we looked at a spatial branching stochastic process with settlement for the metastatic process and introduced a metastatic reproduction number. And this is a paper I will not talk about in this talk. Okay. PDE models, of course, have been used. There's the famous model by Iwata, and basically everything after that is based on Iwata's ideas. For example, Benzicry has now combined this PDE model with methods for machine learning. to look at metastatic data for mice. And then our birth jump process, which I just mentioned, is also a PDE model. And then here in the last block of papers, this is the one which are highly relevant to what I do here, because these one include the immune system now. So the papers by Kuznetsov, Eikenberry, Enderling, etc., they only include the effect of the immune system degrading the tumor, so the anti-tumor effect of the immune system. And the red publications are those which also include a pro-tumor effect of the immune system. Okay. And so in particular, Avner Friedman, he started early in 2006 to look at the macrophages, so the story M1, M2 macrophages, which I just mentioned. Wilkie and Hanfeld, they looked at concomitant resistance experiments. So these are experiments where you take a mouse and you insert two cancer tumors at the same time. And then you see which one grows bigger, the one or the other, or do they grow in parallel? And in most cases, one grows big and the other doesn't. And so there seems to be like a cross communication between the two tumor sites. And so then this one here, these are two papers which we recently published, and this is what I'm going to talk about today. All right. Let's look at one of the effects, which is the metastatic blow-up. So that is the idea. You take out the primary tumor, and then the secondary tumor or the metastatic tumor all of a sudden grows wildly and quickly. And in the literature, there's several theories, and so here I summarize four. Theory one would be resource monopolization. So this basically means that the primary tumor eats more than the secondaries. So if you have cats at home, maybe if you have a big cat and a small cat, and if you give them food, one dish of food, then of course the big cat will eat everything first until it is satisfied. And then the small cat comes and eats whatever is left over. And so that would be the resource monopolization. Immune surveillance, right? So a cancer creates a severe immune response, and maybe just this high immune response shadows over the secondary cancer and keeps it at bay. And then if you take the primary away, then you take the immune response away, and then the secondary can grow. So it makes a lot of sense. Theory three, local promotion, global inhibition. So people were actively looking for a signal which allows, which is sent out from the primary tumor to inhibit the growth of the secondary tumor. And then the last theory four is the immune-mediated theory of metastasis. So that is the theory I talk about here, where the immune system has a pro-tumor role as well. Let's see how far we get in these effects. So all those four theories can explain metastatic dormancy and metastatic blow-up, which means that all of these ideas will play a role in the effect of metastatic blow-up. But only the last one, if it comes to the immune response, only the last one can also explain metastatic to sites of injuries, to sites of chronic inflammations, and also the failure of immunotherapies in some of the cases. Okay. So let's talk about the model directly. So we have two sites. We have a primary site here, a secondary site there. The primary tumor here has a necrotic core, a necrotic center, which stimulates the immune response. And then the first immune cells coming in are those ones here, which are cytotoxic, so they're trying to kill the cancer cells. But then through the interaction with the tumor, they can be educated or adapted, change the phenotype. And we use this doctoral hat here to indicate educated immune cells. And they all of a sudden, they bring nutrients to the cancer, which is here the beaker of milk, and they protect the cancer, which is here a shield, from other immune cells. Now, in the metastatic process, we have the blood circulation involved, and then of course the educated immune cells, they also wander through the blood system, and then they can also come to the secondary site of the cancer. And then here you have a mixture of educated immune cells and cytotoxic immune cells. And then, of course, it's a matter of balance if the secondary site can grow or not. Right. So putting this into equations will give me a system of 8 ODEs. And maybe I'll show you the 3 stages here, which I have in mind. So in the first stage, of course, we look at the full 8 ODEs, and I'm going to show you these in the next slide, and it looks terrible. But this includes all the effects we want to have included. And then we do computer simulations on this one to look at dormancy, blow up, sites of injuries, immunotherapies, and all these kind of questions. But then we can reduce it to a model of 3 ODEs by focusing just on the metastatic side. So here, and this allows us to do a full bifurcation analysis and also a parameter fitting to data for breast cancer and a sensitivity analysis of these parameters. So the stage 1 model, the 8 ODE model, has 70 parameters, where 40 we could find in the literature, but then there's another 30 which we have to guess or make good guesses. In stage 2, we could actually fit all the parameters based on the data which we have. So that was good. But then, being a mathematician, we reduce it even further to 1 ODE, to find a model of 1 ODE using singular perturbation reduction methods so that we can come down to a slow manifold. Yeah, and okay, and so then I'm going to talk about all these 3 stages basically now. So the variables I'm using, I have 2 sites in the first model, the primary and the secondary. UI is the tumor cells, VI is the necrotic cells, XI are the cytotoxic immune cells, so the immune cells which kill the cancer, and YI are the educated immune cells, so the pro-tumor immune cells. And yeah, and so then of course you would have guessed a model of this form where you have all the different interactions that you find important. There's no point in going into detail, but I want to highlight 2 terms, just 2 terms. So one is this term here. So here we have the growth term for the cancer cells. And then this gamma 1 of Y1 is the growth promotion based on the educated immune cells. And so this is a sigmoid function which goes from 1 to 1.5 as a function of Y1, and Y is the educated immune cells. So 1 means there's no effect, and then 1.5 means there's a 1.5-fold increase in the growth rate based on the tumor-educated immune cells. And the other term, right, and the other term is the education term, this guy here, and this shows up here. So this is modeling how the interaction with the cancer promotes cytotoxic immune cells to become educated immune cells. And here this add of UI is just a linear function, bang. So it's basically a Michaelis-Menten term, which we are using there. The biological process of this education is largely unknown. So there's lots of report that this does happen, but how it happens is actually, I think, unknown. Right. Okay, so I mentioned the number of parameters already. So let me look first at the steady states of this model. So the first steady state would be we have no disease at all. So the black line here, the black line is the cancer or the tumor, and this just goes down to 0. And here's the black line for the secondary cancer, which also goes to 0. And then the blue line, this would be the cytotoxic immune cells. And so you have perfect immune surveillance, and the disease is just cured. Okay, so that's a possible steady state. Another steady state is where we only have a secondary cancer here, but the primary goes away. Okay, so this is possible as a steady state of the system. And then another steady state is where you have both. You have a primary cancer and you have a secondary cancer. And both are in steady state. Okay. So let's look at the data and the observations which we were interested in. So this is back to the Kaplan paper from 2005. where the immune cells would come earlier and the cancer cells would come later. And this is something which we can easily reproduce in our model. So the immune cells come first and the cancer cells come later. So there's certainly an effect which is present in the modeling there. Okay. Let's look at primary resection. So this has to do then with the metastatic blow-up question. So here is a time, and then at certain times we take out the primary tumor, and then in this graph we show the growth of the secondary tumor. The dashed black line would be the control case where nothing has been done, and you see that the metastasis would actually grow relatively quick in this case. Now, if you take out the primary, then you get two cases. If you have an early resection, these are the green lines, then the cancer disappears or the metastasis disappears. If you have late resection, which are the red lines, then the metastasis grows. And there might be a significant growth delay, right? So it can be flat for a while and then grows up a little bit later. So you can create some dormancy there. But in those cases, the metastasis comes back. And we will see later, or we will find later a good explanation why this is the case. So let's play around a little bit with the immune response. What does the immune response do in this, in these experiments? So now, again, the black line is the control. But what we include now is that if you take out the primary cancer, you produce an injury from the operation, from the surgery, or from the radiation. So you get increased immune response, let's say for 7 days, right after the surgery. And this is a pink bar right here. And then we, so if we then include the normal, this immune response I just talked about, then we get a long period of dormancy, but then we get growth. If we have a reduced immune response, then this would be this one. We get again dormancy, but then the metastasis seems to die out. And if we reduce the education rate, then the tumor dies out even more quick. Okay, so there seems to be a very fine-tuned dynamic between the education of immune cells from cytotoxic to educated, and also the total number of available immune cells that can be educated. Here's a simulation related to immunotherapy. So what I do here is I show time in days, and the different curves correspond to increasing level of immunotherapy, which we just model by enhancing the group of cytotoxic immune cells. We're giving more and more cytotoxic immune cells. And then you see the control case is here, and then for certain doses here, for a higher dose, we go up here. So the growth is delayed through the use of the immunotherapy. But here it turns around. So then at a certain level, if you further increase the level of immune cells, you actually have a reverse effect. And the cancer seems to grow quicker as compared to a lower dose of the immunotherapy. So this is not a very strong effect in this simulation, but it is an effect which is present. And this might help to explain why in certain cases the immune therapy does not really work. Sites of injuries. So in this model, it's easy to include an injury. So we have the primary on the left, the secondary on the right. And then here at a certain time, we just boost the immune response due to an injury, boost the cytotoxic, actually boost the dead cells. And then after a while, so in this case, it is about 200 days, then we get the formation of a metastasis right there where this injury happened. So in this case, clearly the injury is a trigger for the formation of the metastasis. All right. So that was a full model. Let's come to the reduced model. I think I want to show it completely here. And here the idea is that the primary tumor has basically reached a steady state, and we can focus on the secondary tumor. So now the three equations then only describe the secondary cancer, where U is the tumor cells, X the cytotoxic cells, and Y the tumor-educated cells. And then the combination terms are very similar as in the previous model as well. Okay. Oh yeah. So for this model, I said we did a parameterization based on breast cancer data. And I'm just skipping all of that. So this can be found in our paper, but I don't have time to talk about this here. I rather like to do this mathematical bit and talk about the multi-scale analysis. So what we have here, our three equations are this form. We have an equation for the cancer, and then we have two equations for the immune response, and they act on very different time scales, right? So the cancer grows in a time scale of months or years, very slow, whereas the immune system responds very quickly. It responds in the units of days or even hours. So that motivates, of course, the use of a scaling parameter for the immune dynamics. Or in other words, we assume they're kind of in quasi-steady state all the time. So we do this formally using geometric singular perturbation theory, which allows us then to reduce the dynamics onto a slow manifold. And the slow manifold arises if we set these terms to be 0. So then I write this here as M. So these are all pairs U, X, Y, so that G1 and G2 is equal to 0. So that's a manifold. And I'll show you the manifold in the next slide in a little picture. And on this manifold, we have a one-dimensional dynamics. U dot is F of U of X and Y. And so that's the reduction to a one-dimensional system. Okay, let's look how this looks like. So here, the slow manifold is the green line. Okay, can't see red on red. Anyway, so this the small green line in this left graph. It's an intersection of several manifolds. One is the G1 is 0 manifold, the other is the G2 0 manifold, etc. So I take it out here on the right. So here now, red is the slow manifold, and black is the typical solution. And you see how close they are, right? So you have an initial transient where you jump onto the manifold very quickly, but then the solution follows the manifold very, very closely. And so that's the main idea. So then on the manifold, we are clearly 1D, and so then we have to look at a 1D situation. All right, let's do that. So here. So then that's what happens. So we have a 1D model, so we can use standard phase plane methods, right? So we have a stable steady state here, we have an unstable steady state here, dynamics goes this way or that way, etc. So so this is stuff we teach our students in the, I don't know, first year calculus, maybe not, but rather early. So it becomes a very simple, at least mathematically, a very simple object. Let's see what this does for our applications. So I come back to the primary resection, which I've shown earlier, but now in the reduced model where I reduce it to the one-dimensional case. So then again, here on the left, we have early resection cases where the metastasis decays, and here we have a late resection. Okay. And now on this graph here on the right, I show the corresponding manifolds. So then I need to orient myself just quickly. So here, this would be, okay, no resection. And then this one would be resection. So Anma, I had a change in my voice. Is everything still okay?
Hear you very well, so it's going well so far.
It's all good. Okay, so
yes,
sorry.
yes.
Yeah. So, and I get two different slow manifolds which correspond to the different situation. The upper one in red there is with the primary tumor present, and the lower one is with the primary tumor absent. And what then happens is the dynamics goes up here, sits on the slow manifold, follows the slow manifold, and then the resection happens, and it depends when. So when the resection is late, the dynamics falls onto the other slow manifold and goes to the tumor side. And if the resection is early, it falls to the slow manifold, but it goes down to the tumor-free side and to the cured side. And so here, right in between, there's a saddle point, And it depends on which side of the saddle point you land. Then you either get metastatic growth or you get metastatic decay. And then being a 1D model, we show this also here on the bottom. So this corresponds to the blue line, and this corresponds to the black line. Okay, and then here again is a saddle point. And now it matters on which side of the saddle point you land, distinguishing between treatment success or failure. Okay.
Thomas, can I ask you a question quickly?
Yes.
This critical manifold, is it completely stable? I mean, it's obviously, it seems to me that it's stable. But this fold that you have, I mean, is there some sort of loss of stability or something? No?
Not at all. So
it's completely stable.
You're asking kind of this fold here or something,
yes,
right?
Yeah, exactly.
Yeah, no, this is actually a projection of a 3D picture.
Okay.
Yeah, and it's not a bifurcation picture either. So you can show that these slow manifold is normally hyperbolic always.
Okay.
Okay. So, all right. Yeah, so now I would like to look at the blow-up case a little bit more detail. Oh yeah, what I have not told you, let's go back to the left picture. Now the picture gets more and more busy. You see in the red curves, the cancer, the metastatic grows, but it does not grow bigger than the black. Okay, so the black is the control, it's the untreated case. So you do have a positive treatment effect. The metastasis grows, but it seems to be lower than the black. And this is not what we call blow-up. So the metastatic blow-up is a case where the red one would actually exceed the black one and become much bigger. So then here is a little systematic study where we look at this. In case one, we remove 100% of the primary, and we do nothing else. We do no inflammation increase. We do no increase in the education. And then this would not explain metastatic dormancy or blow-up. Now, if we remove 100% of the primary and allow for an inflammation through the surgery, then this can explain dormancy, but it still does not explain blow-up. This is what I just said here. You do get growth of the metastatic, but you do not get growth which is bigger than it would have been otherwise. So what we have to do, we have to increase also the education of cytotoxic immune cells to be able to actually do get blow-up and do get dormancy like observed. Okay, so this is a new, yeah, I think it's a new result, which we can go back to the clinicians and say, hey, you should maybe look for this mechanism of immune cell education, and if there's any evidence that this is dynamic or that this is increased after a surgery. Okay. So then this case 4 on the slide is another curious case where we have a small primary removal. So this basically means a biopsy. Because so I talked a lot about the immune response, and then if you trigger an inflammation or if you trigger immune activity, you might actually trigger metastasis. So is this relevant for biopsy? Right, in a biopsy, you take out a tissue sample, so you create a little wound, you stimulate the immune response, maybe you actually enhance the process of metastasis formation. If this were true, this would be absolutely terrible. So let's see. So here's a paper, preventing inflammation inhibits biopsy-mediated changes in tumor cell behavior. So they clearly say, if you do a biopsy, you should also reduce the immune response at least for a few days to prevent metastasis from happening. And here, even more so, acute inflammation induced by the biopsy in mouse memory promotes the development of metastasis. So exactly what I just said has apparently been found, at least in mouse experiments. So there are other reports, for example, by the Mayo research, by the Mayo Clinic. So researchers find that cancer biopsies do not promote cancer spread. So that's good. That's good to hear. In particular, it must be said very clearly that biopsies are beneficial for patients because they give a very clear, or often a very clear understanding of what cells are involved in the cancer, and they do help design the best possible treatment strategy. So if I were in this case, I would always opt for in favor of a biopsy than against. But that's not the matter here. The question is, what does our model say about the biopsy question? And so we can include a little perturbance, a little injury somewhere, and see if this leads to blow up of a metastasis at that location. And we scanned our parameter space here a little bit. And we found this blue wedge, this area here, where a blow up based on a biopsy is actually possible. But many things have to come together in an unfortunate way. In particular, the inflammation level has to be rather high. And this phi, unfortunately, I forget what phi is. Sorry. Okay, I can look it up. But the consequence is that in the most cases, you are in the green region where you get basically nothing, or the metastasis stays small. Only in very exceptional cases, it might actually be possible that a biopsy makes it worse.
Is it possible that it could be the size of the biopsy? Phi?
And the size of the biopsy is certainly so this would be right here in the inflammation level.
Inflammation level, okay.
So if you take out more, then you get a larger wound, and then you get a higher response. Okay. All right, so then I think here, this is the last result I wanted to mention. It is again about resection, where in this case, the green ones are actually, why did I flip the colors? Anyway, so the red ones go to 0, the green ones, they continue to grow. And what turned out in our simulations is that you can already look at this very small window here, which we blow up down there, to distinguish between success or failure. Because, because in this area, the red lines stay below the dashed blue line, and the green lines are above a threshold. And so then, what is this? This is about 14 days. No, this is about, let's say 21 days, so about 3 weeks. So it looks like in about 3 weeks after the treatment, you can already make a prediction if you get treatment success or not, or if the metastasis comes back. And so this scale is in years, right? It is in the order of 10 years. But we think that maybe a careful screening 3 weeks after the surgery can already tell you if the treatment was successful or not. Okay. Yeah, so what's the time? Time is perfect. Let me summarize. So I think the pro-tumor effects of the immune system are very important. They are well established in the biological literature, and more is found every day, basically. How this actually happened is largely unknown, unfortunately, and so this is certainly something which needs to be researched further. The tumor education, as we included it, can explain all these 6 observations for metastasis. It's the first mathematical model which can explain all of these in one model, so that's cool. And I think these insights which we gained here, that the pro-tumor role of the immune system is important, could not have been gained without a mathematical model. Right? So I think this gives a level of consistency. It is one hypothesis which explains 6 very different observations. And I think this is a role mathematical modeling can play. So I did not try, as you see, I did not try to write one model for one specific disease. I tried to have more like a meta model, which is more like a, I don't know, like a theory, or like a hypothesis, as I say, that can explain many, many things. But of course, in each cancer and for each patient, you have different details and you have different parameters. So so that's what I see. So it's different from cancer to cancer, different from patient to patient. So here it was not an attempt to model one patient and one cancer, but maybe it can be done. But if you do this, what do you need? So you need a genetic fingerprint of the cancer, but also you need a genetic or phenotypic fingerprint of the immune system. So I think just looking at the properties of the cancer is not enough. I think one also needs to look at the properties of the immune system, which is involved right there. Yeah, And so then that's basically the take-home message. We need to look at the cancer and the immune system at the same time to get the best possible information. Good, then I'm done. Thank you very much.
Thank you very much, Thomas, for a great talk. So the floor is open now for questions. If you have questions, please do. Okay, some people are writing comments. Be brave enough to ask the question yourself. If you want me, I could read it, but please do ask the question yourself.
Okay, I'll ask the question. Is it important to account for cancer stem cells in the model?
Let's see. Cancer stem cells are always important. Right, so you could consider this to be a model for cancer stem cells alone. Right, so we looked at those cancer cells which are able to form metastasis elsewhere. So, and this would typically be stem cells or cancer stem cells.
Any other questions? Okay. Okay, go ahead, Rodrigo.
Thank you. Very nice talk. I was wondering, in the parameter space where we saw the blow up, I found it interesting that it would be in between small and larger tumor sizes. Would you like to comment a little bit on that? I would have expected that parameter space to be more on the extremely big tumor sizes. Maybe I missed something right there.
You mean here?
Yeah.
Yeah, okay. So the red area is the area where you get a big cancer anyways. And so then the biopsy doesn't matter. Okay, so the green area is where there's a little tumor which might grow or not, and you are pretty safe. In the red area, the patient would get a cancer anyways. If you do a biopsy or not, it doesn't matter. And then only in the blue area it matters. So then the biopsy can actually trigger or push you over the boundary to the growing cancer.
All right, thank you.
Okay.
Any other question? Okay, while we're waiting, maybe I'll ask my question. Maybe someone would be get brave enough to ask their ones. The whole idea of a blow up, I'm just wondering, could it be also possible? Obviously I'm not an expert in the field, so I could be talking nonsense here. But is it possible that these several tumors could be growing at different starting points? I mean, you know, there's metastases. So, I mean, one tumor could be big enough and it's growing and it's detected by whatever, like by what do you call it? Different methods, like for detecting tumors. I don't know which one they use in medical.
Medical imaging or so.
Imaging, yeah, some imaging techniques that they use. I think it's called CT scan or C-scan or whatever.
CT scan is possible, right? Yeah.
Okay, so, but the small ones are not detected. So when you actually remove the big ones, it doesn't mean that the small ones are not already growing. I mean, if you keep these tumors without removing them, maybe the small ones are still kind of continue to grow. And this whole idea of blow up is independent of the presence of big tumors in the first place. It's just that happens to be undetected initially. And when you remove the big ones, they actually continue to grow.
And then you do follow-up screens and then you find them again, yeah.
You find them again, exactly.
Yeah. No, I think that's entirely possible. So that they basically act as independent cancers and grow, yeah.
Yeah, okay.
That's entirely possible, sure.
Okay, someone else has a question, just go ahead, please. Itamar, go ahead. You have to unmute yourself, please. Okay, maybe William, if someone else is called William has a question.
Hi. Thanks for your talk. I just had one question about the kinds of pro-tumor effects that you are including in your models. So it seems like you're including tumor effects. Are they all for the transfer of tumor cells between different areas of the body, or are there other pro-tumor effects modeled in your?
So the two major pro-tumor effects is an increase in the growth rate, which is similar or describes the growth factors which are coming from the educated immune cells, and the other one is a protection. So that would be a reduce of the death rate of those.
All right.
Yeah.
Yeah, that's all I have.
Okay, Itamar, do you want to ask a question?
Yeah, I'm not sure that I could read all the 6 points in conclusion 2, to read them one by one, but they seem to me that it's possible that they could be mixed, and then the model will be even more complicated.
You bet, of course, yeah.
But the question is really, in practice, those issues can be mixed in different proportions, in different relation, as you said, from patient to patient and from cancer to cancer and so on. So there is room for Adam and yourself to extend the model now.
Oh, you are right, absolutely. So what we are doing now is we have very detailed data for breast cancer. So we want to now fit it very closely to patient data for breast cancer, for example. Yeah.
Okay, thanks.
Thank you.
Any other question?
Yes, can you uneducate the tumor?
Yeah, that would be good. That would be good. So for that, we need to understand really how it works, how this education is going, and then we can try to inhibit it from happening.
Are you looking at partial ways to partially block the vascularization, which is very characteristic of metastasis?
That's right, yeah. So anti-angiogenesis treatments are certainly important. I think in my context, anti-inflammatory treatments are more relevant. And they are used, right? In some cancers, anti-inflammatories are given together with radiation treatment, for example, and things like that. I think that's the best hope in the moment, to try to control the immune response as closely as we can.
Okay.
Okay, thank you.
Thank you.
Okay, any other question? All right, so thank you very much, Thomas, for a great talk, and we've learned. I'm definitely sure that a lot of people learned a lot from it, and it's perfect for such a seminar series. So thanks
And
for
actually, if you want to ask further questions, just write me an email. I would be happy to answer more.
Okay.